Milliman Lecture Series. And this lecture series is funded by a very generous donation of the Milliman family in memory of Wendell Milliman, who's an actuary. Got his degree here in mathematics. And it's made possible a large fund for inviting visitors. It's a very important step of our department. Many of our visitors are funded directly by matching grants and money from the Milliman Fund. And the highlight of the Milliman Fund each year is the Milliman Lecturer. It's a very selected group of speakers, and we're very honored this year. We have our speaker, Chris, will introduce.
Okay, so first of all, this will serve as a microphone test. Is it okay? Back row? Okay. Okay, so I am Chris Burtzi, and I work at the Department of Mathematics. And I feel a little bit awkward to introduce Martin Heidegger because it's like introducing the Pope. This is the Pope. What else do you want to know? Well, I will try to say a few words. So, what kind of person is Martin? Others are deeply moved by his presence. This comes from a fortune cookie on a Saturday. This is what he got. This was his fortune. So obviously the first thing that comes to my mind is that he was awarded the Fields Medal. For those of you who are not mathematicians, the Fields Medal has the same prestige in the mathematical community as the Nobel Prize in other sciences. Actually, a number of people asked why there is no Nobel Prize in mathematics, and the leading theory is that a mathematician had an affair with Nobel's wife. There's a certain problem with this theory because Nobel did not have a wife. Okay, Martin had a number of other honors, and so let me just mention a few of them. So there were actually 4 prizes based, in a sense, in UK. So Whitehead Prize, Philip Liverpool Prize, Royal Society Wolfson Research Merit Award, and Frelick Prize. Then there was a prize based in France, Fermat Prize. A few years ago, in 2014, he was elected Fellow of the Royal Society. So it's the British or UK, United Kingdom Learned Society. He's also a member of the Austrian Academy of Sciences and of Leopoldina, which is the German Academy of Sciences. And the last thing that I'm going to mention is that he's an honorary Knight Commander of the Order of the British Empire. And some people already started calling him Sir Martin, but it's a little bit too early. He's still, he is not a British citizen yet. He will become soon, and then, yes, you will be able to call him Sir Martin. Okay, so wait a year, personally. A few words about Martin's mathematics. So what I'm going to quote is something that G.H. Hardy said. He was a mathematician. He passed away in 1947, and in 1940, he wrote a well-known essay called A Mathematician's Apology. And this is what he said. I have never done anything useful. No discovery of mine has made or is likely to make, directly or indirectly, for good or ill, the least difference to the amenity of the world. So this is a sort of an extreme view of mathematics as being completely abstract and useless. And this was in a certain context, 1940, Second World War, and technology, and through this mathematics is for destruction. So this is understandable. But then there's this other end of the spectrum where people believe that the mathematics should be or even has to be useful. So I would say that Martin is, from my perspective, still an abstract mathematician, but as close to the other end of the spectrum as possible, because his research is definitely inspired by natural phenomena, mostly from physics. And, well, I cannot speak for physicists or chemists or engineers, but his results definitely help us, as mathematicians, understand these phenomena, at least from our point of view. So this is, from my point of view, the best kind of mathematics, very deep abstract mathematics, which has this extra bonus of saying something about the real world. Okay, so I have to tell you something on the personal side. I am very proud because I have a joint paper to Martin. This has nothing to do with his Fields Medal. But through some work and many meetings, I got to know him, and I will call him my friend, even if he does not approve. So, I can tell you, he's smart. And on the top of that, he's nice. And there are lots of smart people. The mere fact that you are here means that you guys are smart, but it doesn't mean that you're nice. If you would like to meet somebody who is both smart and nice, you will have a chance today in the reception. I will be in Paul Walker Ames room. Everybody's invited. And the last thing that I want to say, this is important because typically what we try to do is to hold all 3 lectures in the same room, and this year didn't work that way. This tells you something about the room situation at this university, although you probably all know about that, right? So anyhow, please know that every single lecture is in a different room. So these are the rooms for the next 2 days. C. M. Smith. And I guess that's it. You would prefer to listen to him rather than to me, so please help me welcome Martin Heiber.
Thanks, Chris, for the very nice introduction. Thanks a lot for the invitation. It's a pleasure to be here, first time in Seattle. You've seen the title of this particular talk. So the 3 lectures will be connected. Of course, there's a thread running through the 3 lectures. They will be somewhat self-contained, hopefully. So it's hopefully possible to get something out of each of the lectures without going to the other ones. It might be more difficult for the last one, certainly for the second one. And the general theme is this sort of bridging scales, which is sort of try to understand how sort of things happening at small scales have effects at very large scales. And the perspective from which we're going to do that is that of probability theory. And so let me first start by saying a couple of words about probability theory. And in particular, so what probabilists tend to do is, well, you have a number of rules for manipulating probabilities, which you're all familiar with. The probabilities of independent events multiply, or sort of disjoint events they add, and so on. But then, in order, you can apply these rules to manipulate probabilities, but then you want to also start from something, right? So you want to assign probabilities to certain events from the first principle or something. And for this, there are essentially, 2 main guiding principles in probability theory. And of course, the first one is going to be very familiar again, which is symmetry. It just says, if you have different mutually exclusive outcomes that are sort of indistinguishable, if you want, from the perspective of the process that produces them, but that are distinguishable to you as an observer of the outcomes, then you should assign equal probabilities to all of these outcomes. And of course, the standard example is a coin toss where you can see whether it comes up head or tails, but from the perspective of the process that produces head or tails, there's no difference between the two, unless the coin is biased, of course, or if you're very smart and you sort of know how you start it off. The second principle is that of universality, and that's maybe probably the physicists in the audience will be very familiar with that principle, but the non-physicists maybe less. And loosely speaking, it says that in many situations when you have many different, somewhat independent or almost independent random events that commonly somehow influence some large, if you want, outcome, then in many cases, if that large outcome is still random, that randomness is somewhat universal in the sense that it doesn't really depend on the details of the small events that produce this large outcome. And of course, historically, the first example of this universality, and that's the one that most of you have seen in your undergraduate lectures, is the central limit theorem, right? Which says, well, for example, if you make statistics of coin tosses, you say you toss a coin 100 times, and you look at how many times it comes up head. So it will be typically around 50 times, but sometimes a bit more, sometimes a bit less. And if you look at the distribution of how it comes up, you get this typical bell-shaped curve, which sort of peaks around 50, and which is called the Gaussian distribution. And in many other situations, exactly the same bell-shaped curve comes up. Right? And so it comes up pretty much in every situation where you somehow basically add up random quantities that are either independent or close to being independent. You somehow add up many of them, and no single one of them has a big influence on the outcome. But they just all together produce this bell-shaped curve. Now, what we're going to see in these lectures are, or what I want to talk about today at least, is mostly not so much about just the central limit theorem, but if you want, other situations where this universality now applies. Of course, the first, again, historically, somehow the first example, which is still very closely related to the central limit theorem, is the discovery of Brownian motion. So, of course, Brownian motion, you probably all have heard of the experiment of Brown, or the observation of Brown, where he was looking at pollen suspended in water under a microscope, and what he observed is that pollen was moving erratically around, even though the water itself was still. And the explanation that was given by Einstein and Smoluchowski in the early 1900s was that, you see, at the time, it wasn't completely clear that matter was made of atoms and molecules. It was around the time where it was, there was more and more evidence that it was the case, and so more and more people were convinced that it was the case, but there hadn't been any sort of conclusive experiment that would really prove it. And so the explanation, assuming that matter is made up of molecules, is that you have these water molecules that sort of move around in all directions, and you have these large grains of pollen sitting in the middle, and every time a water molecule hits the grain of pollen, it makes it move a little bit, right? Of course, each of these effects is imperceptible, right? So the water molecules are really small, so you don't really see the individual hits. But there are many, many, many of these hits, and they happen very, very frequently. And so you see the cumulative effect of these hits, and that's what makes the grain of pollen move in water. And what Einstein and Smoluchowski came up with was a prediction of how far you would see this grain of pollen move in a given amount of time. Okay, so it would say, assuming that you know the size of the grain of pollens and the viscosity of water and so on and so forth, so assuming that you know a certain number of quantities which at the time were known or had been measured to reasonable precision, then you can predict that if you see the grain of pollen at a given location at a certain time, and then you close your eyes, you open your eyes 10 seconds later, it's going to have moved by a random amount, so you can't have a deterministic prediction by how much it will have moved, but you can actually predict the probability distribution of where it will be located, and you can predict somehow the average distance by which it will have moved. Okay? And mathematically, what one sees is that actually if you want the spread of this probability distribution of where the particle is located, right? So if you open your eyes very shortly after closing your eyes, it won't have moved by much, right? And so the probability distribution of where you find it will be very peak around the location where you last saw it. Whereas if you open your eyes only 20 seconds later, then it will have moved by quite a lot, and this distribution will have somehow spread out. And well, in Einstein's theory, the way this distribution spreads out over time is exactly the same as the way heat spreads out in a metal. So you take a cold metal and then you heat it up somewhere. Okay, it becomes very hot, and if you wait for a certain amount of time, that heat is going to spread out. And it's exactly the same equations that govern the two. And well, these predictions, they were quantitative, and they relied, so they had in them the Avogadro number, so they somehow really relied on the assumption that matter was made of molecules. And Perrin then a few years later did actually make the experiment and confirmed the prediction to within a few percent of error, and he got the Nobel Prize for that. So that was somehow the experiment that really settled the fact that atoms exist. Interestingly, somehow the same mathematical object was described a few years earlier by Bachelier in his thesis. So he was a French mathematician who was interested in what we would now call financial mathematics. And so if you want, he was the founder of financial mathematics, so the word didn't exist at the time. And so what he was really interested in was the evolution of stock prices, which apparently has nothing to do with Brownian motion. But then the mechanism that he came up with was very much the same. What he was saying is that, well, what affects a stock price? Well, it's people buying and selling stock. Right? So every time you try to buy some stock, well, it will push the price up a little bit because there's more demand for it. Whereas every time you sell some stock, it's going to push the price a little bit down because there's more offers. Right? And so, of course, if you sell some stock, I think unless there are any multi-billionaires in the audience, it won't have a huge effect, right? So it will be a little bit like these water molecules hitting the grain of pollen, where somehow an individual water molecule hitting the grain of pollen has almost an acceptable effect. But there are many of us who somehow buy and sell stock at the same time, and so it's the cumulative effect of all of these trades that make the stock price move. And again, he came up with this idea that, well, therefore, somehow the probability of where you find the stock price at a later time should be governed by the heat equation. So he came up with exactly the same equation governing the stock price as, in two completely different contexts, right? So that's, if you want, one of these instances of universality, somehow where you have two apparently wildly different contexts, but when you make a story from it, you see the similarities in the story, and then you can actually turn this into really quite quantitative predictions that are actually essentially identical for the two. Right? So that's another general idea. Yeah, so here, actually for the small story, so he was really, so that's the only picture I found of him. I haven't seen any picture of him at any older age on the internet. I think he never really got a permanent job. He got a job, I think, somewhat relatively early on. He got a job in the Sorbonne, but then he was drafted because World War I broke out. And then by the time he got back, there was no job for him anymore. And then by the time he got his first real job was actually at the age of 57 or something. And it was, I don't remember where it was, maybe Besançon or something like that. It wasn't in Paris. So So it was because at the time, somehow the French probabilists really didn't take him very seriously. So we thought, okay, this is really not proper mathematics somehow. And so the proper mathematics, so here the description, you see, it was a sort of very coarse description of what's going on, where you just say, well, for example, I see that particle somewhere at a certain instant of time, I close my eyes, I open my eyes sometime later, what is the distribution that I see where I could see the particle at later times? Mathematically, one thing that a much more precise description would be to have some kind of mathematical object that actually describes the trajectories of these particles, rather than just the knowledge of where you might or might not find them. And this was really first done by Wiener in the late 20s, who was a professor at MIT. And so he was the first to really formalize this in the sense of, in the mathematical sense of building a probability measure on the space of continuous trajectories, which has the property that, whenever you look at the type of observations that I described earlier, they are governed by the heat equation. And so that's now called either Brownian motion or the Wiener process. And so here is an example of what you actually see. So the way this would, so here you would have time horizontally, and somehow the location of your particle vertically, and well, if your particle is in 3 dimensions, it would be just one of the coordinates. And so you see this very erratic kind of motion, where the particle somehow moves left and right very rapidly. So let me give you a movie. So here, this is an example where you take this trajectory, you just take one single trajectory that goes, say, from some very large negative time to some very large positive time, and you look at larger and larger scales, so you just zoom out, right? So it's one single trajectory, and you just sort of zoom out more and more. I could run it backwards, and so you would sort of zoom in more and more, same thing. What you see is that you always end up, it always looks the same, right? So you can run this movie for as long as you want, it will always more or less look the same. The reason for drawing these two parabolas here is that in order for the movie to look stationary, so in order to always see the same, what you have to do is when you zoom out, say by a factor 4, somehow horizontally, you have to zoom out only by a factor 2 vertically, rather than also a factor 4, right? So the way of zooming is that, sort of the ratio between, you don't keep the ratio between the horizontal and vertical axis constantly. Vertically, you only zoom out at the square root of, but you zoom out horizontally. And so that's somehow. So what this kind of tells you is that in some sense, this curve behaves everywhere a little bit like a square root. Right? So it's and that's what you see when you see this very jagged motion. Okay, so we say that this is so it's a kind of fractal curve, if you want. You say that it's self-similar with exponent a half, where the half refers to the half of the fractal. And of course, since the works of Wiener, there have been many works, so Donskoy was maybe one of the first, that somehow mathematically prove that there are many, many situations in which this Brownian motion really shows up naturally. Right? So it's a very natural process that you can get as somehow scaling limit of many other processes. Meaning, you take some process which is not this Brownian motion, but which is somehow built from a mechanism which is somewhat similar to the mechanism that governs the stock prices or governs the physical Brownian motion Brown observed, and you take that process, you somehow zoom out. If you zoom out sufficiently far, it will somehow look closer and closer to Brownian motion. Maybe I should close the door. Okay, so here we were just talking about a process which was a function of time, and you just had somehow one-dimensional curve. So what about higher dimensions? Well, so here is a somehow two-dimensional analog of a random walk. So a random walk would be the simplest way of producing a Brownian motion, which is, say, toss a coin, and if it comes up head, you make a step to the right, and if it comes up tail, you make a step to the left, and you just keep on doing this. You always move by one, either up or down, or left and right. And then you look at what happens on somehow larger and larger scales, and what you see converges to this Brownian motion. So in other words, since coming up head or tails has equal probabilities, it's exactly the same as simply picking an arbitrary function which has the property that nearby values differ by either +1 or -1. So that somehow the difference between nearby values is exactly 1 in absolute values, either 1 or -1. And just pick one of these functions randomly with equal probability, and then what you see is this Brownian motion. So a two-dimensional analog would be the following. So take a two-dimensional lattice, for example, this honeycomb lattice, which is bipartite in the sense that there's a way of coloring it. So here there's half the points are red, half the points are blue, in such a way that blue points are always next to red points and vice versa. And they would correspond to like even values and odd values. And so now you can look at all possible ways of assigning an integer value to each of these nodes. And now you can, again, look at all possible ways of assigning an integer value with the property that nearby values have to differ by exactly +1 or -1. Right? So that would be like a two-dimensional analog of this random walk. And of course, you need this to be bipartite in this sense, because otherwise such a function just doesn't exist. Okay? But if it's bipartite, such functions exist. And then you can ask yourself exactly the same question. So what does that look like when you look at larger and larger scales? And here it already gets much less easy first to describe what the answer is, and then to actually prove any theorem. So for this particular model that I just described, the answer, mathematically, the answer is still not known. Of course, the answer is known in the sense that everybody knows what the answer is supposed to be, but it's not known in the sense of having a mathematical proof that shows that the answer is really the correct answer. Okay? So there's a conjecture, and everybody in probability believes that the conjecture is true, and you can simulate things, and you can just match it to the conjecture, and of course it matches. But to the best of my knowledge, in this very simple example, there still isn't actually a proof that the conjecture is true. And so what happens when you look at larger, so here this on the left is an actual simulation of this model. So I took a grid which was maybe 1,000 times 1,000 or something, and I drew a random such function according, which changes only by ±1, and then I just color it. It gives me a coloring according to the height of the function, and that looks like this. And so you see, it also looks somehow very rough in a way. And what I did on the right is I simulated what is called the Gaussian free field, which is, now this time it's actually not a random function. So what happens here is that the conjecture is that when you look at what happens at larger and larger scales, what it converges to is not actually a random function, but it's only a random distribution, which is some sort of generalized form of function, but which in a way is allowed to blow up, in some sense, at every point simultaneously. And what you do here is, well, simulate this object on the computer, and, well, you can see that this somehow more or less looks like the same thing. So in some sense, so what I wrote up here, so this is still a Gaussian object in the sense that, okay, you're not really allowed to evaluate this at points because I said it's not a function. But what does actually make sense is averaging the value of a little circles or squares or whatever you want. Right? So you should think of this as being, well, on every pixel you draw the color sort of corresponds to like the average value of this in that little square. And then these averages, again, are distributed according to a Gaussian distribution, so according to the standard bell-shaped curve. It's just that this time it has the property that if you average on some sort of smaller and smaller disks, well, if it were a function, right, then somehow if you take averages on smaller and smaller values, these values should converge to something. So here they don't. So if you average on smaller and smaller values, the values just sort of keep on drifting between very large positive, very large negative values that just get larger and larger, and it doesn't really converge to anything. And that's related to the fact that sometimes you can describe this object completely by its covariance, so by somehow the correlations between what you see at the point and at some other points. And these correlations are supposed to behave logarithmically in the distance between the points, and in particular, if the points are very close to each other, the logarithm actually goes to infinity. Right? So if you take the points the same point, quickly you get infinity. Anyway, so this is another one of these natural objects that show up. So here, for the particular little model that I explained to you, nobody knows how to prove that it converges to this object when you look at it at large scales, but there are many other models that are somewhat have somewhat the same flavor, where people are able to prove that they converge to this object. Okay, and it's really the same object that shows up for many, many different models. So this is in some sense like the two-dimensional analog of Brownian motion, and in the same sense there is a sort of d-dimensional analog of Brownian motion for every dimension. So there's a three-dimensional analog as well, etc. And they become wilder and wilder in a way that sort of the values, if you try to evaluate them at points, they somehow oscillate in a worse and worse way as the dimension gets large. But so in both cases, the examples, so let me actually show you a little movie of this. So this here is like a movie version of this. Okay, so there are models which also evolve in time and which have the property that somehow at fixed time it would look like this free field, but there's actually a time evolution. And so again, there are many, many different models that have natural time evolutions, and in many cases what you end up seeing on very large scales is something that looks like the movie that I just showed you. Now in both cases, these were somehow free objects in the sense that, for example, here we just looked at all possible functions, which are values that differ by plus minus 1 on neighboring sides, and we didn't make any a priori, we didn't provide any sort of preference about which kind of functions we prefer and which kind of functions we don't like. We just say, well, just pick any of them with all the same probability. And then you have these objects that show up that tend to be described by Gaussian distributions. Now there are other situations where you have other natural objects of the same type that show up that are not free and that are not described by Gaussian. So the simplest example is what's called the Ising model, which is a model of magnetism, if you want. And so here, what you do is, well, again, it's a two-dimensional model because it works well for pictures. So what you do is that you say at every point on this lattice, you take either the value +1 or -1. So this time it's not that the difference of the values is +1 or -1, it's just the values themselves is either +1 or -1. But instead of, now if you were just choosing one configuration like that randomly, that wouldn't be very interesting, right? I mean, you would just have +-1s that are sort of distributed half-half, and you wouldn't really see much structure, and if you somehow look at it on large scales, it would just look kind of uniform. So what you say is, you say, well, I prefer configurations where neighboring values are the same. And one way of doing this is to say, well, the probability of seeing a given configuration, so a configuration is a way of having plus ones or minus ones at every sign. That probability isn't the same for every configuration, but it's actually proportional to this quantity here, which actually just basically measures, so here, this twiddle here means x and y are neighbors, and so it just measures how many neighbors have the same sign, right? Because if they have the same sign, the product of the values is plus 1. If they have opposite signs, the product of the values is minus 1. And then you put a positive number here in front, and you exponentiate. So it means that if many values have the same, right? So if many neighboring sites have the same value, then this quantity is much bigger than if many neighboring sites have opposite values, right? So you try to favor somehow having the same value. But on the other hand, of course, there are many, many more configurations where neighboring sites tend to have opposite values, right? I mean, if you just take a typical configuration, if you just take a configuration completely at random, typically neighboring sites will actually have opposite values, right? There won't be that many sites that have the same value. So there's some sort of a competition between the fact that you want to make it more likely that neighboring sites have the same value, and the fact that, well, there are many, many more of these configurations where the values actually differ. And it turns out that, well, depending on how you choose this parameter here, it's either one of the effects that wins, or it's the other effect that wins. Right? And so this parameter is some sort of a temperature, and here is what happens at high temperature, and so that's where the effect that, in some sense, many configurations tend to have opposite values wins. So here is the case of small beta. So small beta corresponds to large temperature. And so here what you see is more or less the same as what you would see if you simply draw a configuration at random without caring at all of whether things are aligned or not. Whereas at low temperature, which is the large value of beta, then this alignment somehow takes over. So what you tend to see is that you see most of the values are the same, and then there are just a few of them that are kind of outliers that have the wrong value, right? So here you see most of them are yellow, there's a few of them black. And of course, sometimes you would just see the opposite picture where most of them are black and there would be just a few yellows in between. Physically, you actually see that. So in a magnet, that corresponds to a transition where a magnet loses its magnetization. Because if you take a magnet and you heat it up, at some point it actually loses its magnetization. There's a temperature at which it loses its magnetization, and that corresponds exactly to going from here to here. Okay, so that would be the magnet at room temperature, where things tend to be aligned, and so then it actually creates a magnetic field. And then when you heat it up, at some point it gets into this kind of configuration where everything is disordered, and then you don't really see any magnetic field anymore. And what's interesting is what happens in between, right? So there's going to be one temperature, which is the one where there's an exact balance between these two effects. And then you see something like that, right? And there you see something which is somehow an interesting kind of fractal structure. So here you see a configuration which has somehow, structure at all scales. You have somehow sort of large yellow regions with some black inside. There are also large black regions with yellow inside. But if you looked at what happens at even larger scales, well, this large yellow region would actually be inside an even larger black region, which would be inside an even larger yellow region, etc. So you have this kind of structure at all scales. And then you'll be interested, so that's the one which is really the interesting one to study mathematically, right? And so you can ask yourself, if I take such a configuration and you look at what happens at very, very large scales, does it converge to something? What is the scaling exponent, somehow the analog of the 1/2 in the one motion in this case, etc. So in this particular case, there is actually a theorem which is very recent, which says that indeed, there is a scaling limit. So there have been conjectures from the physicist's point of view. This is a model that has been solved, in some sense, was solved back in the 40s. But then, okay, so then somehow already quite some time ago, Cardi, for example, gave, to some extent, characterized very much what you expect to be the large-scale limit of this object. And recently there's been a mathematical proof that this limit is indeed the thing that we see. And in this case, this limit is not a free limit. So there's no Gaussian distribution showing up. So if you, for example, so the distribution is, it's again one of these distributional limits where point-wise it doesn't make sense, but averages somehow make sense. But this time, if you look at one of these averages and you look at its distribution, well, okay, it's still going to roughly look like some sort of bell-shaped curve, but it's not going to be a Gaussian distribution. So in particular, one somehow knows that it really has tail behavior which is different from the Gaussian one, etc. Now, here is another example on which there has been quite a lot of mathematical progress recently. And so the situation here is interface growth. So you think of a two-dimensional situation where you have two different regions that are separated by a sort of one-dimensional interface. And one of the regions is more stable than the other one, and so the stable one kind of wants to invade the unstable one. So this interface moves. And what you're interested in is really the fluctuations around the kind of average motion. So there's some average speed at which the interface is going to move. But then there will be some random fluctuations, and you're interested in the behavior of these random fluctuations. So here are two experiments. That one, I think, is sort of a sheet of paper that you actually burn. And this is the position of the flame from successive times. And here's an experiment where you take a liquid crystal, and it's a liquid crystal that comes somehow in two phases. One is stable, one's unstable. You prepare it in the unstable one, and you zap a laser beam at it. That sort of makes it flip over into the stable phase where the laser beam hits it, and then that one invades the unstable one. And you sort of take pictures 10 times a second or something, and color here is time. So this is sort of a superposition of these pictures. And you can come up with, many sort of mathematical toy models that are supposed to describe that kind of situation. Okay, so here are somehow numerical simulations of 3 different kind of mathematical toy models that describe this situation. And for those of you who were at Chris's seminar, the model he talked about in the seminar just earlier on is this one. Okay, and so here are pictures of 2 other models of the same type. And okay, one can see that numerically they somehow behave more or less in the same way. One can measure things, and one can see that the large time behavior is actually more or less the same. But you would like to have a mathematical proof of this fact. So here, very recently, there has been a theorem by Pastel, Matetsky, and Remenick, where they show that for one specific mathematical model, which is this one actually in this picture, there is indeed somehow a limiting object at very large scales. So you look at larger and larger scales, it converges to something if you rescale in the right way. And they have a complete description of what you actually see on these large scales. And again, the limit has nothing to do with Gaussian distributions. And actually, it has somehow something to do with the distributions that come up in random matrix theory, which seems completely unrelated to this situation in principle. Now, you see, so you have these various kind of situations. And, well, you see the common features. So you have one type of situation. You can come up with many different mathematical models that describe a situation of this type. And then the natural conjecture is that for all of these mathematical models, you sort of see the same thing at large scales. and typically there's no theorem. Or there are theorems for very, very specific models. So there's like maybe like here, there's one model for which there's a theorem, and there's 100 other models for which there's a conjecture. And so one would like to be able to say somehow something about these things that are mathematical theorems rather than conjectures. Okay, so here, let me just list a few properties of these objects, right? So the sort of objects that you see in the limit, so they will always be scale invariant because they were obtained by rescaling something, and so they have to be themselves invariant under the operation of rescaling. The scale invariant. They usually have some type of Markov property, which means that if you look at what happens in a region, then it only depends somehow on what happens on the boundary and not on what happens outside. Okay? It comes from the fact that in all of these situations of when there is interaction is sort of local or somehow short range. Then they tend to have somehow translation invariance because you start from models that are translation invariant. If you want to be able to say something, often you have rotation invariance. So then you can make a leap of faith and say, well, you guess that you have conformal invariance, because that's somehow like the infinitesimal version of rotation and translation invariance. So in 2 dimensions, this buys you a lot, because in 2 dimensions, conformal invariance is a very, very large symmetry group. And so there is quite a lot known in the 2-dimensional case, right? So I mentioned earlier on for this Ising model, there are recent theorems, but only in 2 dimensions. 3 dimensions, almost nothing is known. So that buys you a lot, and there is all this recent work on stochastic Löwen evolution and quantum Löwen evolution and loop soups and so on and so forth, and this is all somehow probabilistic objects that exploit conformal invariance in 2 dimensions. Outside of 2 dimensions, almost nothing. So there is this one example I just gave you of the interface growth models. I said that there's this very, very recent result where people gave a characterization of what you see at large scales for one model. That's pretty much the only example. So that doesn't sound very good for mathematicians. So here's a situation where you can actually say things. Right? So the Gaussian case is better understood. Right? So if the limit is somehow described by these Gaussian objects, then, well, these are very easy to describe, and someone knows quite a lot about these Gaussian objects. And it's somehow these non-Gaussian objects that are very badly understood. And so you can ask yourself, well, what happens if I'm, in some sense, close to a Gaussian object in the following sense? So now, in all the examples that we had earlier, what you did is you had just one model, and then you look at what happens at very large scales. And then you ask yourself, is there a limit? So now take a family of models that has a parameter in it, and which has the property that there's some value of the parameter for which you have a good handle of what happens at very large scales, and what happens there is Gaussian. And then if you take the parameter away from this value, you don't know anymore what happens. Expected, you have one of these conjectures. Applies for which there's no value. And so now you can ask yourself, well, can I take some kind of a joint limit where I let the parameter converge to the value for which I know what happens, and it becomes somehow Gaussian, but I simultaneously look at larger and larger scales, and I look at the scale which is sufficiently large so that I actually see something that deviates from the Gaussian behavior. And then you can ask yourself, what do you see there? And is what you see there, again, somehow universal in the sense that you expect to always see the same thing for pretty much every model? So the situation here is picture, here's a picture where you should think of the screen as being like the space of all possible models, mathematical models for a given physical situation. Right? So it's of course not a 2-dimensional space, it's some sort of crazy infinite dimensional space that you don't even know how to formalize. And the arrows are somehow the operation of zooming out. Okay? And then these objects that you're really interested in, they are sort of fixed points, right? Because they are the objects that don't change anymore when you zoom out. Okay, so they are somehow fixed points. And now imagine you have a situation where you have two of these fixed points. One of them, which is Gaussian, that would be that one. So here is a picture which corresponds to this interface fluctuations, and there's one which is called the Edwards-Wilkinson model, one which is this KPZ fixed point, which is the one that corresponds to growth models. So suppose you have this situation where you have two of these fixed points. One is Gaussian, and so you have some idea of how to describe it and which models have that behavior when you look at large scales. And one is non-Gaussian, and then maybe you don't know very much about it, and you maybe don't even know the correct exponents, and you don't know how to describe it. And now what you can do is you can take a family of models where some models converge to this Gaussian fixed point at large scales, and some models converge to this other fixed point which you don't know how to describe. And you take a joint limit, right, where you somehow make the model somehow converge to a model that converges to that guy, but you look at sufficiently large scales so that you're actually away from this fixed point. Right? So then what you expect is to be basically on this line here. Right? So it's a line which, if you go backwards, you would go to this fixed point, and if you go forwards, somehow go to the other fixed point. Okay, and then, so the conjecture, but this time it's, to some extent, it's a mathematical theorem. The conjecture is that what happens in various situations, this line is really a line in the sense that, it's not obvious, since this picture was supposed to be in some very large infinite dimensional space. There are many ways of connecting two fixed points. It's not clear that it's somehow by a line or even by something finite dimensional. It turns out that in many cases it is actually connected by something maybe just 1 or 2 dimensional, so something quite low dimensional. And these objects tend to be described by somehow simple, relatively simple looking stochastic partial differential equations. So here we're talking about models where there's a time evolution. Okay, so a bit like the movie that I showed you earlier. And well, the first equation I wrote down here is the one that is supposed to govern these interface fluctuation in the situation where they're almost symmetric. So where there's almost a symmetry somehow between the two, where, if you want, the two regions are almost equally stable. Okay, so if they are equally stable, then the interface doesn't really move on average, but it might still fluctuate. And then one expects the fluctuations to be Gaussian. And if they are almost equally stable, then it still moves in the preferred direction. And one expects the fluctuations to be described by this equation here, the KPZ equation. And there's a similar equation that governs actually a situation of this easing model, or somehow more generally models of magnetization in a situation where you somehow nearly mean field, which means in a situation where instead of just interacting with neighbors, you somehow interact with sites on a kind of large, relatively large distance. Now, okay, so now you can ask yourself, can you prove something? So what is there to prove? So what would a theorem even look like, right? So the sort of theorem that you would like to prove is something along the lines of what I showed you of these pictures, right? So take a reasonably natural model, a reasonably natural class of models in one of these situations that depends on a parameter, and take a joint limit where you set this parameter to a certain value, and you zoom out at the correct scale, and then what you expect is to see something that coincides with the solution to one of these equations, right? And this should be true for, sort of as large as possible class of models, and you should expect to get the same equation for all models in that class, right? So that's the sort of results that we're after. And there's a problem with that, and the problem is a very basic problem, which is that, well, if you want to prove a result like that, the first thing you need to know is whether, what does it actually even mean to be a solution to these equations? And there's actually a serious problem with that, because if you take, for example, this KPZ equation, so it involves the square of the slope of the solution. So let me show you, where is it? Here. Okay. So this here is a simulation of the solution of this equation. Okay? And so this is what it looks like at fixed time. And so now, well, you see, first you see it really looks like this Brownian motion I showed you earlier, and that's actually a theorem. And so, well, in particular, I told you early on that this Brownian motion really sort of looks like a square root at every point. And so you see here you have this sort of like this square root type behavior around every point. And so in particular, it tells you that the slope is actually infinite at every point. And that's also a theorem in the sense that you can show that there's no point at which it's differentiable, and it's really only holder continuous with exposure less than a half. And so then this equation is completely nonsensical, right? Because the right-hand side actually involves the square of the derivative, and I just told you that the slope is infinite at every point. So the square of something which is infinite, clearly infinite. And it's sort of a bad infinity, right? I mean, in the sense that somehow just having infinite slope, you would think, yeah, okay, but maybe it's sort of, in some sense, it's a big oscillations between plus and minus infinity, so it sort of cancels out in some sense, right? But okay, once you square it, you can't talk your way out of it. And there's also a similar problem here, which is that the solution to this equation, that kind of looks like this. And it's again one of these very flickerish things, so it looks a little bit different. It looks a little bit like this free field I showed you earlier at small scales. And again, I told you that this free field has this property that when you try to evaluate at a point, it doesn't really want to be evaluated. It sort of just starts, if you take smaller and smaller averages, it just starts sort of fluctuating more and more. And so it doesn't want to be evaluated at points. And so then what does it mean to take the cube? The solution, right? You can only take the cube of a function that you can actually evaluate. Right? If you can't evaluate it, it doesn't mean to take the cube. It doesn't mean anything. So you've written down an equation which sort of looks, a priori it looked like a nice equation, but then it turns out that it's actually nonsensical because you have infinities all over the place. And so it turns out that in these cases, well, there are these constants over in this equation. And it turns out that they have this funny property that, well, you can actually, in some sense, choose the value of these constants to be the right kind of infinity to create cancellations between these terms. So here between this term and this one, and here between this term and this one. So that actually there still is a meaning to these equations, and there is a notion of solution to these equations. Okay? And that's somehow going to be the main point of the next two lectures. So let me just show you the kind of result that you want to prove. Right, so here is first the result. So this is just a result at this stage for showing that there is indeed a clean somehow notion of solution for these equations. And of course, if you want to get a notion of solution to this equation, you can say, well, okay, so I can somehow approximate it by something. And I want to show that these approximations converge to something. But then you want to make sure that whichever way you approximate it, you always converge to the same thing. And that will certainly be delicate here because you have these infinities that have to somehow cancel out in such a way that what's left is always the same thing somehow, whichever way you approximate things. And that a priori looks like that's not going to be possible. So you will need certainly some kind of assumptions. And so in general, all these equations had somehow this kind of shape. So there was a linear part, which is like here, this heat equation part. Then there's some nonlinear terms, which I just wrote, which somehow depend on the solution, maybe on the derivative or something. And then there is some noise term. So here this psi, in both of these examples denotes space-time white noise, which you should sort of think of it as having independent random variables at every point in space-time. And that's the thing that makes the solutions very irregular, right? Because if you think of having independent random variables at every point, well, that's something that oscillates like crazy. And so you feed this into some equation, but it's not unreasonable to expect the solutions to also oscillate like crazy. And so that's really the reason why these things are badly behaving. And so, well, now we have a very general theorem which actually says that you take an equation of this type, and there are some assumptions on these nonlinearities, but they are reasonable assumptions. I mean, they are reasonable in the sense that when they are not satisfied, you really expect the systems to behave in a very different way. So it's really it's a physically relevant assumption and not just a mathematically convenient assumption. Okay, so you have somehow really relevant assumptions somehow on these nonlinearities, but if they are satisfied, and they're satisfied with the examples I just showed you, then there is a kind of canonical notion of what it means to be a solution to this equation. And for example, you can obtain these solutions in the following way. Since the problem is that this psi is like independent random variables at every point, and that's very irregular, what you can say is, well, I replace it by something which is actually nice and smooth, and has the property that if 2 points are more than epsilon away from each other, then it's independent. But if they are less than epsilon away from each other, then it's actually just some nice, smooth interpolation or something, right? So then you have a perfectly nice notion of solution. And then what you want to do is you want to somehow modify this equation in a way that depends on the value epsilon in the same way as here. Here what it means is you want to choose these constants here to depend on this value epsilon in such a way that goes to infinity, as epsilon goes to 0. And then the theorem is that there's a way of doing that in such a way that you do get a limit, and the limit is the same whichever way you approximate your white noise by something else, as long as it's in a stationary way and it satisfies a few sort of relatively reasonable conditions. Okay? Now, in general, so there's some subtlety here. It's just that in general, what you get, okay, so you get some kind of notion of limit, but what you really get is a notion of, you have a family of limits. So there's a family of notions of solutions, and it's the family which is canonical, and not the solution itself. And in this case, it would correspond, there's a one parameter family parametrized by the value of this constant. Okay? So you get a one parameter family of solutions, and the family is canonical, but the parametrization, if you want, is not canonical anymore. So, right, so that's what I mentioned here, is that actually there's a, in general, so in these two examples that I showed you, the parameter is just this big constant. In general, you might have more than one constant showing up, and the way these things are parametrized might be somewhat non-trivial, which is what is mentioned here. And you can show that these things are very stable in the sense that you have some kind of continuity with respect to the way that you approximate things. Okay? So you can look at many different ways of approximating these equations by adding terms that formally look small, but if you actually compute their size, become very big, and still the effect in the limit is to just, if you adjust parameters so that you converge to something, you will again converge to a member of this canonical somehow family of solutions. So it's very stable in the sense that you can mess around with these equations in pretty much any way you want. There's of course going to be some ways which simply won't make them converge to anything, but if you manage to make them converge to something, they're always going to converge to a member of this family of solutions. Okay? So in that sense, it's very stable. It's like if you manage to converge to something, you always converge to an element of that family of solutions, or you might just not converge to anything. And this is really related to this notion of universality, right? Which says that, you know, you can take many different models, okay, that are somehow in the same kind of class that, you know, is described by something which is similar to one of these equations. And as long as you're somehow close to this Gaussian situation, if you rescale things in the right way, you're always going to converge to one of these somehow solutions to one of these equations. Okay, so this is it's a very closely related notion, and you can actually make that precise in the sense that there are, you know, a number of examples now of systems where, you know, you can do exactly the kind of joint limit that I mentioned earlier on, where you have a parameter, you send the parameter to a value, you zoom out to the right scale, and what you see there is then, you know, one of these solutions to one of these equations. Okay. So I wanted to explain a little bit more how this works, but I think I stop here for today. And thank you very much for your attention.
Are there any applications to this in neuroscience as it deals with neurotransmitter like communication?
Not that I know.
What kind of no-code groups do you get showing up in? So, you know, how can you compute the dimension from the dimension of the space you're living in, or?
Yeah, so the dimension here would, so it's somehow related to the number of constants that show up in your equation, right?
Okay.
But actually, of course, it's somehow, typically it's larger, it can be larger because the same constant can be combined, made out of somehow different components of the group. But yeah, so there's actually, so tomorrow in a way, we're going to explain a bit more about that in a different context, but it's very closely related. But yeah, it's very explicit.
So you mentioned the Markovianness of the interactions between the elements and whatever model you're looking at. Does this kind of analysis extend to models with long-range connections as well?
Yes, so some of, right, so the kind of analysis that then gives, you know, equation of that type, that doesn't really exploit this Markovian structure. Actually, I think one doesn't. Yes, so again, in the two-dimensional case, people are able to really exploit this Markovian structure, and that somehow it's related to this domain Markov property that shows up in SLE. In the other cases, I'm not sure, at least mathematically, I don't think that one is really able to actually exploit the Markovian structure. So you can. So it would be very natural, right? So you would want to write down some kind of conjectures that say, you know, there's only one space-time Markov process which is scale invariant and translation rotation invariant, and which has, you know, these and those scaling exponent. It should be the one which gives a scaling limit of whatever. And so you would want to be able to prove these kind of results. These sort of characterization results, which really say that there are few of these objects. And that's only known, I mean, in one dimension, of course, it's known, and basically the only objects that run in motion are these alpha-stable Levy processes. And if you impose kind of moment conditions, they'll really just run in motion, and that's it. And you would want to have a similar kind of rigidity result in higher dimensions, but that's not known at all. At least mathematically.
If you consider a mathematical object and you're studying it at large scales, you define all these invariant properties to it. How do you go on study the nature of these invariant properties when you go from the macroscopic scale to the microscopic scale?
Well, so typically at microscopic scales, these properties are typically not true, right? So I mean, so where was it? So that slide, right? So you have these properties that you expect to see for the scaling limit, but they are only true somehow approximately or in large scales. So they are just not true at the microscopic scale, right? So they don't survive. I mean, they just sort of emerge when you look at what happens at large scales. You know, just because if your interaction is somehow relatively short range, well, that short range, by the time you zoom out, it becomes zero. So it's just these kind of properties.
Can we study, like, when we actually start going from large scale to smaller scales, can we study how these properties evolve?
I mean, are you not sure what you're referring to? I mean, the thing is that there's, of course,
Taking that inverse, basically, your talk was on going from micro to macro, and the question is, how do you take the inverse transformation?
yeah, but okay, so, but in that case, so if you take one of these objects, okay, so their behavior at small scales is somehow easy to describe in the sense that at small scales, the behavior is the one that you obtain by simply deleting the nonlinear part. And so then at small scales, they become Gaussian and so on. Right, so it's still, you see, so it's what you see in this picture. So the red line going backward, going against the arrows means going to small scales. Right? And going with the arrows means going to large scales. And so here what you see is when you go to small scales, you see again something which is scale invariant, but which is Gaussian and more well understood. And actually, when you try to, when you want to give a notion of solution to these equations, what you have to do is you actually look at higher order objects that describe what happens at small scales, where this Gaussian one would just be the first one in some kind of hierarchy of objects that tell you what the behavior is at small scales. So in that sense, one has a very, very good understanding on how these behave at small scales.
So you said these one parameter families are continuous in both of their arguments, and then you said something about what kind of continuity it is in the noise parameter. Can you say something about what kind of continuity you get in the field parameter?
Oh, so here the field is just an initial condition, right? I mean, so these are evolutionary equations, right? So there's a time evolution, and so it's kind of stable. It doesn't depend too much. If you perturb the initial condition at time 0, then it doesn't have much of an effect, right? So it's really, and that's in some kind of Elder type norms or Sobolev type. I mean, standard kind of norms that you get from functional analysis.
I'm always curious how physicists are smart enough to get the right answer. You mentioned a lot of situations where they are totally right, and everybody believes it. I'm just curious how you see the mathematician's job. Is it that their arguments are totally right but too hand-wavy, and so we should fill in the details? Or are they really geniuses on some other plane and will be able to verify what their arguments really about? I mean, how do you see, are their intuitions helpful at all on the mathematical side, or are they totally too hand-wavy to make use of?
It's mostly
all the cases of physicists conjectures that were wrong.
well, I mean, there are cases of conjectures go wrong, right? It's just there are cases where you have a conjecture of something and it's the opposite, because one of them will be right, wrong eventually. just look at the right paper. But sort of by and large, I mean, once physicists form a consensus on something, they tend to be right. So there are situations where you just don't form a consensus, and then, well, you will typically have papers claiming the thing and the opposite. So one of them will be right, one of them will be wrong. You just
so like, where do they come up with these equations? Where does the equation come from? Is that
oh, okay. So these equations.
Schrödinger equation or this kind of thing?
So they come from basically being the simplest equations that we can write down. If you want? No, but it's
okay.
But it's not stupid. I mean, there's really a reason why and it comes with the fact. So here you can actually guess this, and this is really, so there also the physical intuition really helps, which is you can actually guess which terms should be the terms that show up by just looking at how formally the equation behaves on the changing scale.
Okay.
Right? So you just look at how the equation behaves on the changing scale. And then what you see is that, for example, so here in this, so look at just the first one. Okay? So if you drop this nonlinear term and you drop that constant, so you just have the heat equation plus this noise, then that one is scale invariant under a certain way of rescaling things. Okay? So you rescale it and you get exactly the same equation back. But then if you add terms, so now you say, well, it's supposed to be a model for interface fluctuations, right? So now whether the interface is here or here, it shouldn't really make any difference to how it moves, right? So the equation shouldn't really depend on the position of the interface, but it should really only depend on the shape, right? So that already tells you that the nonlinearity should depend on derivatives of h and not on h itself. And then you say, well, I write down all the monomials I could write down that depend on derivatives of h. Okay, so then there's one which is simply the derivative of h. That's the simplest one. But that one, well, first, if you have an interface fluctuation model, it's kind of reasonable to expect that it's symmetric under doing this kind of symmetry. And then that term wouldn't be symmetric under that symmetry, and so you can discard it. So then the next simplest one is this one. And then you can say, well, okay, so you could have a power 4, for example. Right? So now, if you take a power 4, and you do that rescaling, which keeps these bits the same, then the coefficient of the power 4 as you go to larger scales becomes smaller. Whereas the coefficient of the power 2 as you go to larger scales becomes bigger. Okay? And that somehow, that's the sort of arguments that tell you that the power 2 should have an influence at large scales and the power 4 shouldn't have an influence on large scales. Of course, it's still sort of hand-wavy and dodgy because, you know, of course, these things are all infinite, and so you're really sort of talking about sort of relative sizes of infinite quantities. But still, that's essentially the argument. And that argument really works. I mean, in the sense that, you know, whenever you rely on it, you get the right answers.
So don't you think that there will be also some component of physical reasoning, like, you know, the second derivative, where it is just Laplacian, where you expect sort of spread according to the heat equation?
Yeah, so that one, well, it's again, because somehow if you take, you know, you can, it's again like the dominant term in a certain expansion, right? I mean, you can start with pretty much anything you want, and then, you know, at some point the Laplacian will show up as the simplest term, and then you will have higher order terms with all the higher order terms scale in different ways.